Let's start section 1.5, elementary matrices. We've talked a little bit about inverses. We said that a matrix is invertible if there's a matrix B such that for matrix A times B is equal to B times A, which is the identity. We learned that a matrix, if it has an inverse, then that inverse is unique, but we never really found any inverses. That's what we're going to do in this video. We're going to start with a really easy example, and we're going to find the inverse of it. Here we have 1, 1, 1, 2. This is a 2 by 2 matrix. It's going to be one of the easiest examples to find the inverse of this. So what is the inverse? Well, if we call this matrix A, 1, 1, 1, 2, then there should be a matrix B that's also 2 by 2, such that A times B is equal to B times A, which is the identity matrix. And the identity matrix is a 2 by 2 matrix that looks like this, 1, 0, 0, 1. For this first method in figuring out the inverse, what I'm going to do is I'm just going to put letters in for these entries here because I don't know what they are. I'm going to put A, B, C, D. And let's focus on A times B. So A times B is going to be equal to 1, 1, 1, 2 times A, B, C, D. And we want that to equal this 1, 0, 0, 1. So what I'm going to do is for the left-hand side of this equation, I'm going to calculate it and see what I get and the relationships between A, B, C, and D in order for it to be this identity matrix. Okay, so let's figure out the left-hand side. That is, if we multiply these two matrices, we get A plus C, B plus D, A plus 2C, and B plus 2D. This is going to equal 1, 0, 0, 1. So from here, we can say that A plus C is 1, A plus 2C is 0, B plus D is 0, and B plus 2D is 1. All right, well from here I see that B is equal to negative D, and then I can plug it into this one and I get D is 1. So D is 1, and since B is negative D, I get B is negative 1. I found two of these letters. Now let's focus on this side. So here I see that A is equal to negative 2C. So if I plug that in, I get negative C is equal to 1, which tells me C is equal to negative 1. And then since A is negative 2 times this, A is equal to 2. So we figured out our matrix. Let me erase this so I have some room. So we see that B is equal to 2, negative 1, negative 1, 1. And you can double check this. You can see that A times B will be the 2 by 2 identity matrix. And you really only have to check the right-sided inverse because you'll get this one for free. But you can check that one as well. So this is one way to find the inverse of this matrix here. We're going to talk about a different way a little bit later on. So let's move on. The next thing I want to discuss is, does every square matrix have an inverse? The answer to this is no. Let's look at a really basic example, a 2 by 2 matrix. So all I have to do is show that there exists one matrix that does not have an inverse, one square matrix. If I can show that, then that tells me that not every square matrix has an inverse. So what about this one here, 1, 1, 1, 1? We can use the same idea as the last one, but you'll see if I multiply this by A, B, C, D, and I want it to equal 1, 0, 0, 1, I'll get that A plus C, B plus D, A plus C, B plus D. This is equal to 1, 0, 0, 1. So A plus C is equal to 1, but at the same time A plus C is equal to 0. B plus D is 0, and then B plus D is 1. There's no way that A plus C can equal 1, but at the same time equal 0. And the same thing with this one. B plus D can't be 0 and 1 at the same time. If you subtract this from this one, you'll get that 0 is equal to 1. Or 0 is equal to negative 1, and you'll get a false statement. So this matrix does not have an inverse. This is not invertible. When we have a matrix that's not invertible, we call it singular. So let me write this down because you're going to see it in the book and also in your homework and on a test. A non-invertible matrix is called singular. An invertible matrix is called non-singular. So you can call a matrix that has an inverse, you can say it's invertible, or you can call it non-singular. Most of the time you'll see this word. It's just another word that means invertible. So you'll see non-singular. And another word for non-invertible is singular. Okay, let's move on. And this is just a repeat of what I said. An n by n matrix that does not have an inverse is called singular. Here's an interesting question. Suppose A is n by n and B is n by n, and these matrices are invertible. So both of these matrices have an inverse. I'm not saying that B is the inverse of A, I'm just saying that both of them are invertible. Is A times B invertible? And if so, what is the inverse? Okay, let's see if we can solve this. Now we know A is invertible, so that tells us that we have this inverse, A to the negative 1. We know B is invertible, so B to the negative 1, that's going to be the inverse of B. And we want to see if A times B has an inverse. So this product, A times B, does this inverse exist? Well, notice that A times B, if we multiply it with B inverse times A inverse, let's see what we get. Well, this is equal to, these parentheses, I can move them around. This is going to be B times B inverse times A. So I got rid of these and I just moved these two over. But B times its inverse is the identity matrix. And the identity matrix times any matrix, A, this matrix A is itself. So then we get, oh sorry, I dropped the inverse here. So we get A times A inverse. Make sure you can see that. Because this had an inverse, so I just popped it back on. And then A times the inverse is the identity matrix. So we just showed that the inverse, the right-sided inverse of A times B, is B inverse times A inverse. Well, what about let's check to see what we get when we take B inverse times A inverse and multiply it with A times B. Again, we can move the parentheses. This becomes the identity. You can put parentheses around this one and get B, and you're left with the identity, which is n by n, because all of these matrices are n by n. So this one is also n by n. So what we've shown is that this matrix, which is A times B, if we multiply it by this product, we get the identity. And at the same time, if we switch those orders, we also get the identity matrix. So in conclusion, we see that A times B, its inverse is equal to B inverse times A inverse. So this is sort of like that transpose rule we saw earlier, a few videos ago, where we had like A times B transpose is B transpose times A transpose. We switched the order. So you can't just distribute this, you have to switch the order as well. So this shouldn't be too hard to memorize because we had something similar for the transpose. So be careful. When you have a -1 like this, so when we're taking the inverse of a product, we don't just send the -1 in, we also switch the order.